The XOR gate is a digital logic gate that implements an exclusive OR, that is, a true output results if one, and only one, of the inputs to the gate is true. If both inputs are false or both are true, a false output results. XOR represents the inequality function, i.e., the output is true if the inputs are not alike, otherwise the output is false. A way to remember XOR is one or the other, but not both. XOR can also be viewed as addition modulo 2. As a result, XOR gates are used to implement binary addition in computers. A half adder consists of an XOR gate and an AND gate. Other uses include subtractors, comparators, and controlled inverters. The algebraic expressions and both represent the XOR gate with inputs A and B. The behavior of XOR is summarized in the truth table shown on the right. Symbols. There are two symbols for XOR gates: the traditional symbol and the IEEE symbol. For more information, see logic gate symbols. The logic symbols and can be used to denote XOR in algebraic expressions. C-like languages use the caret symbol to denote bitwise XOR. In these languages, despite the similarity of symbol, pass gate logic wiring, an XOR gate can be constructed using MOSFETs. Here is a diagram of a pass transistor logic implementation of an XOR gate. Note: the RSS resistor prevents shunting current directly from A and B to the output. Without it, if the circuit that provides inputs A and B does not have the proper driving capability, the output might not swing rail to rail or be severely slew rate limited. Alternatives: if a specific type of gate is not available, a circuit that implements the same function can be constructed from other available gates. A circuit implementing an XOR function can be trivially constructed from an XNOR gate followed by a NOT gate. If we consider the expression, we can construct an XOR gate circuit directly using AND or a NOT gates. However, this approach requires 5 gates of 3 different kinds. An XOR gate circuit can be made from 4 NAND or 5 NOR gates in the configurations shown below. In fact, both NAND and NOR gates are so-called universal gates, and any logical function can be constructed from either NAND logic or NOR logic alone. As an alternative, if different gates are available, we can apply Boolean algebra to transform as stated above, and apply De Morgan's law to the last term to get which can be implemented using only 3 gates as shown below. More than 2 inputs. Strict reading of the definition of exclusive or observation of the IEC rectangular symbol raises the question of correct behavior with additional inputs. If a logic gate were to accept 3 or more inputs and produce a true output if exactly one of those inputs were true, then it would in effect be a one-hot detector. However, it is rarely implemented this way in practice. It is most common to regard subsequent inputs as being applied through a cascade of binary exclusive OR operations. The first 2 signals are fed into an XOR gate, then the output of that gate is fed into a second XOR gate together with the third signal, and so on for any remaining signals. The result is a circuit that outputs a 1 when the number of 1s at its inputs is odd, and a 0 when the number of incoming 1s is even. This makes it practically useful as a parity generator or a modulo 2 adder. For example, the 74LVC1G386 microchip is advertised as a 3-input logic gate, and implements a parity generator. Applications. Uses. In addition, the XOR logic gate can be used as a 1-bit adder that adds any 2 bits together to output 1 bit. For example, if we add 1 plus 1 in binary, we expect a 2-bit answer, 10. Since the trailing sum bit in this output is achieved with XOR, the preceding carry bit is calculated with an AND gate. This is the main principle in half adders, and the combined and XOR circuit may be chained together in order to add ever longer binary numbers. Pseudo-random number generation. Pseudo-random number generators, specifically linear feedback shift registers, are defined in terms of the exclusive OR operation. Hence, a suitable setup of XOR gates can model a linear feedback shift register, in order to generate random numbers. Correlation and sequence detection. XOR gates produce a 0 when both inputs match. When searching for a specific bit pattern or PRN sequence in a very long data sequence, a series of XOR gates can be used to compare a string of bits from the data sequence against the target sequence in parallel. The number of 0 outputs can then be counted to determine how well the data sequence matches the target sequence. Correlators are used in many communications devices such as CDMA receivers and decoders for error correction and channel codes. In a CDMA receiver, correlators are used to extract the polarity of a specific PRN sequence out of a combined collection of PRN sequences. A correlator looking for 11,010 in the data sequence 1,110,100,101 would compare the incoming data bits against the target sequence at every possible offset while counting the number of matches. 1110100101 11010011 20 bits 1110100101 111010 50 bits 1110100101 1110 1110 20 bits 1110100101 1110 1011 20 bits 1110100101 111010 1000 40 bits 1110100101 111010 1111 0 bits matches by offset. 1 2 3 4 5 In this example, the best match occurs when the target sequence is offset by 1 bit and all 5 bits match. When offset by 5 bits, the sequence exactly matches its inverse. By looking at the difference between the number of 1s and 0s that come out of the bank of XOR gates, it is easy to see where the sequence occurs and whether or not it is inverted. Longer sequences are easier to detect than short sequences.